Bohr proposed a model, and these were his assumptions. Okay.
So you wrote 1931.
Yes, sorry. I think somehow I'm always drawn to 1931. Because that's when Dirac proposed the Dirac equation, which predicted the antimatter. Okay, so 1913, Bohr's assumptions were the electrons in the atom say follow some the electrons in the atom form a set of discrete and stationary states. Okay, stationary states. What do I mean by stationary? In physics, a stationary state is something where there may be motion, but that motion does not lead to a decay of energy. Okay, that is what we call a stationary state. So in more detail, what Bohr envisaged was that the electrons, orbit the nucleus in non-radiating orbits in the form of ellipses and circles. Okay, circles around the nucleus. Well, yeah, that's kind of given. All right. Now, the fact that these orbits are non-radiating was an assumption. Okay, so it just basically by fiat, Bohr said that they cannot radiate, and that's why Bohr's atomic model is part of what we call the old quantum mechanics, because the old quantum mechanics still had some assumptions which seem very arbitrary. I mean, any physical theory must have some fundamental assumptions, right? Otherwise, it's not a physical theory. That the atomic orbits are arbitrary is one of those assumptions. Now, if it turns out, this assumption explains, the simple atoms such as hydrogen extremely well, but it fails to describe the more complicated atoms, even like the helium atom, and therefore, the old quantum theory had to be replaced by the new quantum theory. So, okay, let me just say this, that this was an ad hoc assumption. I should say this was an ad hoc assumption.
So when Rutherford said, if Rutherford said the same thing, like the electrons would be non-radiating and will form a stable orbit, will he have one less failure?
No, I don't think so. I think Rutherford was basically, in physics, pointing out important flaws in the theory is as important as, forwarding new, solutions, right? I mean, Rutherford, I think he was given the Nobel Prize for his discovery of the structure of the atom, right? So, if I'm not mistaken.
Okay.
I mean, physics, science is done incrementally, right? So, Yeah, I mean, Rutherford was, using data that he had gathered himself, right, through his experiment. I don't know if the data about the spectral radiation data was already there, but Rutherford wasn't. Yeah, I don't think he was a quantum physicist. He was more of a classical physicist. Okay, so this is assumption number one. So Bohr's second assumption number two, is that so there are these stationary states, and the electrons can make jumps or transitions, between these stationary states. Okay. In a way, we cannot predict classically. So it's a by assumption, it's a classical physics cannot predict this. Okay. And these are what we call quantum jumps. So if, say, En is greater than Em with both, say, En and Em being stationary states, then if the electron jumps from, say, En to Em, then Bohr said that it'll emit a photon, but the frequency of the photon would be given by the difference between these two energy states divided by Planck's constant, h. Okay. So,
Sir,
yeah.
was this like influenced by the photoelectric effect, or like was it wholly
Yeah.
independent?
No, it was completely predicted by photoelectric effect.
Ah,
Yeah, Einstein and Niels Bohr were very good friends, and also enemies in some sense, because not enemies, but later in life, they diverged on their views on quantum mechanics, right? Bohr was an ardent supporter of quantum mechanics. Einstein, later in life, did not rejected quantum mechanics. And when Einstein was visiting, Einstein's doctor told him that he could not smoke. So when he could not have tobacco. So whenever he went to, there's a famous episode where he would like sneak into Bohr's office so he could steal tobacco from Bohr. Anyway, so and he got caught. Okay, so this is basically what happens when the electron jumps from a higher energy level to a lower energy level, and the inverse process. Sorry, that's Kali in the background. The inverse process is where an electron, say, oh, sorry, I can't write today. In which the electron in, say, the energy state Em jumps to En by absorbing a photon of frequency nu. So this, rule is called the Bohr frequency rule. Okay. All right. Any questions so far?
So the sun's luminosity, is that the same effect as this electron jumping, the sun's light?
No, it's something different. It's comes from a nuclear process, not from. I mean, I'm sure there are atomic transitions, but that's not a dominant process. The dominant process is nuclear fusion, and that's basically you have to go to nuclear physics for that.
Okay.
And the idea there is that so suppose that you have a proton, another proton, a neutron, another neutron, say, coming together. If the pressure is very, very high, they can fuse into a helium nucleus, right? And some part, but the mass of the helium nucleus is less than the mass of 2 protons and the mass of 2 neutrons, okay? So there is an energy difference. So, why, that comes from this process. And that energy is converted into radiation through E equals to mc squared.
Well, I asked this question because they measure the spectrum of sun's light, so I thought that would be this spectrum as well.
Right. The spectrum is different from, so this will basically produce radiation, right? And then the radiation will travel outward from the inside of the sun. And when the radiation is traveling outward, what will happen is that it'll interact with the gas. Okay? It'll interact with the gas. And the gas would be excited to high energy states, and then it would relax. So the gas itself would also be producing secondary radiation. And so if you now do a spectral analysis of this light, you will see the lines which are typical of the gas that makes up the sun. So the answer is that yes, you will see in a spectral analysis, you will see the gas, which the signature of the atomic transitions of that gas, but the main process that drives the sun's engine is nuclear fusion, which is of course driven by the sun's gravitational force, because under the gravitational force of the sun, the gas that makes up the sun, it collapses on itself, and that drives out the temperature up. And when the temperature reaches a critical number, a critical threshold, that starts all the nuclear fusion process. Okay.
Yes, sir, understood.
Okay. All right. So, I said that Bohr assumed that there was some kind of discrete stationary states, but how do you determine what those stationary states are? So for that, Bohr did something which may seem a little bit arbitrary, but what he said that, these elliptical orbits or these circular orbits will have some sort of, angular momentum, right? So they will have some angular momentum. And if P is the angular momentum, so P phi means it's an angular momentum, then Bohr said that this is quantized. This has to be quantized in units of n h bar. Remember that h bar is h divided by 2 pi, and n is some natural number. Okay. So this is what Bohr, assumed. He basically, now you can see why the fact that h bar has the dimension of angular momentum, comes in handy, right? And you might say, okay, this seems a bit arbitrary, but basically what Bohr said, and I think either Bohr's idea inspired this, or Bohr was inspired by this idea, is that Wilson and Sommerfeld said that if you have a periodic system, then if you look at the phase space of the periodic system, then the area of the phase space is quantized. And the area of the phase space is going to be something like dq, and I think if you can choose your generalized coordinate to be an angle, and that Sommerfeld said has to be, Wilson and Sommerfeld said has to be an angle. And this basically is inspired by this formula. Sorry, has to be NH. Yeah. Okay. So that if P phi was independent of phi, then you would have 2 pi in the denominator. I'm sorry, Kali is being so naughty today. I don't know why. Oh, he wants to go out. All right, so so this is basically, we will see soon that this condition is essentially what allows us to determine what those energy levels are going to be. Okay.